So for presentation number 3, I decided to choose option A, which was exponents. Exponential notation. Exponential notation is most often written as a to the nth power. For positive whole numbers, n would be in the set z plus, or z positive, which is the set of positive integers, or you could consider it the set of whole numbers excluding 0. So exponents work similarly to multiplication. So 3 times 4 is equal to 3 added 4 times. So 3 times 4 will be 3 plus 3 plus 3 plus 3. So similarly to that, 3 to the 4th is equal to 3 multiplied 4 times instead of added. So 3 to the 4th power would be 3 times 3 times 3 times 3, which is equal to 81. In more general terms, a to the nth power is equal to a times a times a n number of times. Multiplying exponents. If you are attempting to multiply two numbers in exponential notation and they have the same base, you can add the two exponents and combine them into one base. If they had different bases, you wouldn't be able to simplify them at all. For example, if you had x to the 6th power times x to the 7th power, you couldn't simplify that at all, and the exponents and numbers would just stay separate. But if they have the same base, you can combine them into one. And the notation for that, for multiplying exponents, is written as a to the mth power times a to the nth power is equal to a to the m plus n power. The notation for multiplying exponents comes from how we write out the expanded version of exponential notation. So, again, we have a to the mth power times a to the nth power is equal to a times a times a m times, also multiplied a times a times a n number of times. So you have m number of a's and n number of a's. So you would add them together to get a to the mth power times a to the nth power equals a to the power of m plus n. Here's an example of multiplying exponents. So here we have x to the 4th power times x to the 5th power. So this is equal to x to the power of 4 times 5, which is equal to x to the power of 20. Dividing exponents. If you are attempting to divide two numbers in exponential notation and they have the same base, you can subtract the two exponents and combine them into one base. So this is very similar to multiplication, except instead of adding the exponents, you are subtracting them. And again, if they did not have the same base, there would be no way to simplify the numbers in exponential notation. So the notation for dividing exponents is written as a to the mth power divided by a to the nth power is equal to a to the power of m minus n. The notation for dividing exponents comes from how we write out the expanded version of exponential notation. So a to the power of m divided by a to the power of n is equal, so here we split into numerator and denominator. So in the numerator we have a times a times a, m number of times, and in the denominator we have a times a times a, n number of times. So we can then split the numerator and denominator. So we'd have a times a times a, n times, and 1 over a times 1 over a times 1 over a, n number of times. So we have yet to define this, but 1 over a is the same as a to the negative 1st power. Again, we will define it later. But this gets us to a times a times a, again, m number of times, and a to the negative 1 times a to the negative 1, n number of times. So that gets us to m times minus n times. So a to the power of m divided by a to the power of n is equal to a to the power of m minus n. Here's an example of dividing exponents. So we have x to the 6th power divided by x to the 4th power, which is equal to x to the power of 6 minus 4, which is equal to x squared. Exponents of exponents. If you are attempting to simplify a number already in exponential notation that has another exponent, for example, a to the power of m to the power of n, you can multiply the two exponents together. So the notation for taking the exponent of an exponent is written as a to the power of m to the power of n is equal to a to the power of m times n. The notation for taking the exponent of an exponent, yet again, comes from how we write out the expanded version of exponential notation. Here we have a to the power of m to the power of n is equal to a to the power of m n number of times, which we are used to. But then we have to simplify each a to the mth power on its own. So we have a times a, m number of times a times a times a, m number of times. So we have a m times n times. So we have m n number of times, so that would be m times n. So that's how we get a to the m power to the nth power is equal to a to the power of m times n. Here's an example of finding / simplifying the exponent of an exponent. We have x to the 7th power to the 3rd power is equal to x to the power of 7 times 3, which is equal to x to the power of 21. 0 as the exponent. So, earlier I said that we defined exponents for the set of z positive, or the positive integers, or the set of whole numbers not including 0. So, we need to define a to the 0th power for cases such as a to the nth power times a to the negative nth power, which would equal a to the n minus nth power, as we know from multiplying exponents. And that would be equal to a to the 0th power. So we define a to the 0th power as equal to 1, so which I state more clearly below. And now we need to figure out why. So this comes from our need for a to the 0th power to fill in the position of 1 in multiplication/division scenarios, meaning a to the 0th power has to be the multiplicative identity. So we have a to the nth power times a to the 0th power, which would equal a to the nth power times 1, which is equal to a to the nth power. So we see that a to the 0th power is acting as the multiplicative identity. Stated another way, focusing more on how we can multiply exponents, we have a to the nth power times a to the 0th power is equal to a to the power of n plus 0, which is equal to a to the n. So in both cases, whether or not we assume that a to the 0 equals 1 or not, we see that a to the 0th power is acting as the multiplicative identity. Negative exponents. So despite already using negative exponents to define dividing exponents and to define 0 as an exponent, we need to actually define what negative exponents are. So we know that the inverse of multiplication is division, and that the multiplicative identity is 1. We also know that a to the 1st power equals a, and that a times 1 over a is equal to 1. From multiplying exponents, we know that a to the 1st power times a to the negative 1st power is equal to a to the power of 1 minus 1, which is equal to a to the 0th power, which we now have defined as equal to 1. So putting it all together, a to the negative 1st power must be equal to 1 divided by a. The standard notation of negative exponents is a to the negative nth power is equal to 1 divided by a to the nth power. And yet again, this equation comes from our expanded definition of exponential notation, while also making use of the exponents of exponents notation. So we have a to the negative nth power is equal to a to the negative 1st power to the negative nth power. So that's kind of using the exponents of exponents, but backwards. So we have 1 over a times 1 over a times 1 over a n number of times. So if we restate that, kind of combining the denominators, we have 1 over a times a times a n number of times. So that would be equal to 1 over a to the nth power. Here's an example of a negative exponent. A to the negative 4th is equal to a to the negative 1st power to the 4th power, which is equal to 1 over a times 1 over a times 1 over a times 1 over a, which is equal to 1 over a times a times a times a, which would therefore be equal to 1 over a to the 4th power. In the shorter version, it would appear as follows. It would simply be a to the negative 4th power equals 1 over a to the 4th power. The middle steps are just to make it more clear how we get to the final product. Rational exponents. Rational exponents are directly related to roots. Rational exponents can be defined as such. A to the power of 1 over n is equal to the nth root of a, or in more notational form, you see the nth root of a. It comes from the concept of exponents. For example, we know that the square root of a to the 4th power is equal to a squared. So if we also take a to the 4th power to the 1/2 power, that is equal to a to the power of 4 times 1/2, which is equal to a squared. So a to the 1/2 must be equal to the square root of a, or more explicitly, the second root of a. Here we have another example. A to the 12th power to the 1/3 power is equal to the cubed root of a to the 12th power, which is equal to a to the 4th power. We can also have a fraction without 1 in the numerator as a rational exponent. In this scenario, the rules of multiplication and division with numerators and denominators, respectively, still apply. For example, we have a to the 9th power to the 2/3 power, which we can separate out the 2 from the 2/3 just to get 1/3. So we'd have a to the power of 9 times 2 to the 1/3 power, which would simplify to a to the 18th power to the 1/3 power, which would then be equal to the cubed root of a to the 18th power, which is equal to a to the 6th power. And we know this is true because if we just multiply 18 and 1/3 together, we get a to the 6th, but we get the same thing if we do the cubed root of a to the 18th power. Irrational exponents. So this is more difficult to define because it makes less sense with roots and exponents and just whole numbers. It's not quite the same, but we can define irrational exponents by using rational exponents that are close to the irrational one and finding what they converge to. So, for example, we know that pi is equal to 3.141592 and so on. We also know that 3 is less than pi, but pi is less than 4, and that 3.1 is less than pi, but pi is less than 3.2, and 3.14 is less than pi, but pi is less than 3.15, and so on. And we can just keep going like that with more and more decimal places. So if we were trying to find 2 to the power of pi, we would actually be calculating something that isn't pi, because pi is irrational, but we'd be taking 2 to the power of a rational number that is close to pi. So in this case, we'd probably go more decimal places than this, but I have us calculating the 2 to the power of a fraction, which is 2 to the power of 6,283 divided by 2,000, which is equal to 2 to the power of 3.1415, which is approximately equal to 2 to the power of pi. So that's how we would figure out irrational exponents. We would just take something that is close to that irrational number and make that the exponent instead. And that's how we sort of understand how irrational exponents work, because the concept behind multiplying a number an irrational number of times just doesn't quite make sense. And these are my sources. Thank you.